So let's talk about relative velocity. Okay, so relative velocity. There's kind of two categories of relative velocity problems. We'll call them riverboat problems and Superman problems. And I think what we'll do is we'll just start with an example. Okay, I think that's the easiest thing to do. So let's imagine this. You have a river. Okay, and this river has a current in it. All right, and we'll make up a value for that current. Let's say it flows at 2 meters per second to the south. Okay, and then let's say that there is a person attempting to row a boat across the stream. All right. In the first scenario, this person is not going to try to correct for the stream. They're just going to paddle, or row, I should say, directly across. And what we would expect to have happen is, as they are rowing across, that river's current is going to alter their direction, right? So basically what we have here is we have the rowing vector plus the current vector. Now let's give them a value for their rowing speed. How about, I don't know, 3 meters per second. Okay, so if they row at 3 meters per second easterly, and the river flows at 2 meters per second southerly, we add those two velocity vectors together, okay, and we get this resultant vector that is somewhere at an angle towards the south from east. Now, who observes this? Well, the person who is standing on shore, or us from our high vantage point. Okay, from the person in the boat's perspective, if they just look at the water, they're just rowing across the water, but the water's carrying them along as they're rowing. Okay, so much like if you were to walk across a travelator at the airport. So this just becomes sort of a standard vector addition problem as it stands. It gets more interesting when you try to correct for that, but let's just do it as it stands right now. Okay, so the first thing we want to do is we want to know what their resultant vector is. Okay, so the resultant velocity then is going to be, just using Pythagoras to sort out that value, and then using trigonometry to figure out at what angle we're talking about here. So that is an opposite over adjacent value, so we want the inverse of that, opposite over adjacent. Okay, and I'll just do that math and we'll come back. All right, so just going through and doing the math, you get a value of 3.6 meters per second, 34 degrees south of east. Okay, let's add something to this now. Let's say that this river is 1 kilometer across. Okay, 1 kilometer across. Okay, actually, what I'll just throw in here, say that that was question A and it was find resultant V, and then B is, if river is 1 kilometer wide, find time to cross. Now, it's a really easy way to do this, okay? It's essentially just this. So time is going to be equal to your distance divided by your speed, or distance divided by velocity. So your velocity in the, we'll call this the x direction, right? The x plane, we'll call this the y plane, right? Pretty standard way of naming these things. Your velocity in the x plane, right? And your distance is in the x plane. So those two are just going to match up together, all right? So basically we have 1,000 meters and we have 3 meters per second. That of course will give you 333, actually 0.3 seconds. Now this bothers some people, right? They're like, yeah, but you didn't go straight across. You actually went in this direction, right? So to prove it to them, what we can do is we can say, okay, well, let's figure out then, if we actually go across here, how long that's going to take. But remember, we're now dealing with a value that's larger than 1 kilometer, aren't we? Okay. So let's just prove it that it is legitimately 333 seconds, and that you only need to concentrate on the x value alone. Okay. So first we got to figure this out. All right. So what we have here is we've got a 30. It's actually be a little more precise so we get the same value. It's about 33.7 degrees, that angle. And this is 1 kilometer. Okay. We want to know, what is this distance right here? This is 33.7 degrees. Okay, so we're just looking at our trig here. The cosine of theta, right, is equal to adjacent divided by the hypotenuse. And we just rearrange that, right? To find the hypotenuse, we take the adjacent, we divide it by the cosine of theta. If we want that in meters, we just simply convert it to meters, divide by the cos of 33.7. See what that gives us. So we get 1201. Actually, it kind of is more close to 1202. 1202 meters. Okay, so we're traveling a distance then of 1202 meters at a velocity of 3.6 meters per second. So again, time equals d over v, and what we're expecting is a very similar answer to what we had there. It should be the same actually, but due to rounding error, it might not be quite exactly the same. Maybe 3, 3, 3. And the point is slightly different, but that's just rounding error. Okay. I don't know why I put a -1 on my second. There should be a -1 on there. That's the time it takes. Okay. So remember, values that are in the x direction or the y direction purely, you can just work with them together. If you want to do a bunch of extra work because, I don't know, it feels good or you're that type of person, you can go through finding the actual distance along here. But remember that the velocity along here is actually higher. Okay, so that's a basic riverboat type problem. The second thing here that I want to do though is now I want to correct for the flow of the river. Okay, so a secondary problem you might get with this is correct for the flow such that you travel directly east. Okay, so now the setup is a bit different here. So let's think about what we're going to have to do. So here's your river. We've got our, I don't want it to look like that. We've got our flow like this, right? So now what we're saying is we want the person in the boat to go directly across. They have a maximum velocity of 3 meters per second, okay? So what we want to have here is we want to have the result. We want to have the result of what we do be directly across, right? So we want our resultant to be this. So we need to end up with this, all right? So we need to end up with that. So what that means is, what our gut should tell us, is that we need to head kind of in a northward direction somehow, like up here, right? If we head up here, and then we add in that vector for the flow, and we add our vectors tip to tail, the resulting value should be the straight across that we're after. So essentially what we're thinking about here is we are flying. We're rowing into the current a little bit so that it pushes us back on course. So we'd say this is an on-course, trip. All right. So let's fill in some values and see if we can figure out what we're doing here. Now, where does the 3 meters per second go? Does it go here or does it go here? I think it goes here. If you think it goes here, you're correct. Okay. The person can row at 3 meters per second with respect to the water, and that's exactly what they're doing. Okay. So from their perspective, they're rowing kind of like diagonally upstream. This is still 2.0 meters per second. Okay. So if you were only asked to find what heading they would take, you would go ahead and you would solve for this. So tan theta equals opposite over adjacent. Figure out what heading they were going to go at. And sorry, I actually want to do this. Sorry guys, it's not tan. It's a Monday. Sorry, that's sine. My mistake. We want opposite over hypotenuse here. Sorry about that. Good catch. That's better. Opposite over hypotenuse. Nice one. I was like thinking in my head, it's like, I know it shouldn't be the same value as it was before. Okay, so this works out to 42 degrees. Well, let's be a little more precise. 41.8. Okay? I know I'm not obeying sig figs quite correctly, but let's just be as precise as we can. If we're really worried about it, let's add another 0 on here just because. Okay, so heading 41.8 degrees upstream, okay, will bring us into a course directly across. All right? Now, question B, how long will it take? And I'm going to ask you this. Will it take greater than, less than, or equal to this value? Or less than, greater than, or equal to the way I've written it. Just think about that for a second. So everyone voted that it'll take longer. And the reason why is because now in my x direction here, I'm now traveling more slowly, right? So how fast am I going? Well, I'm going 3.0 meters per second times the cosine of theta, right? Because this is the hypotenuse and this is the adjacent angle, and this is the value that I need to look at in order to figure out, and this is the actual direction I'm really traveling. I need to figure out how long it'll take based on the cosine of this value. So 3 cos 41.8 equals, I get something like about 2.2 meters per second in the cross direction there. So then to find time, of course, got to take the full 1 kilometer divided by the value that I'm traveling in that x direction, which is actually my true trip, right? My true direction, my true velocity based on this observer. Okay. You get about 454 seconds. So it takes longer if I were to make sure that I go directly across and correct for that value.